Okay, chapter 20 practice. I have 4 problems. The last one has 3 parts, so it will take advantage of all of our equations that we outlined in class. So I will give you the question, tell you what equation we use and why we use that equation, and then I'll show you how I solved it. Okay, so first question, solve for delta S of the system when 1108 joules of heat is removed reversibly at 200 degrees Celsius. Okay, this is of heat. I should have specified. So you should see heat. Whenever you see heat, you should think Q. Okay, so what are the parts of this problem that allow you to be able to identify the particular equation that you need to use? The first is delta S of the system. So that's pretty obvious that you need to choose an equation that solves for delta S. So remember, delta S of the system is synonymous to delta S of the reaction. Okay, so anytime you look at the equation page on the exam, you would see 2 different ways to solve for delta S of the system. So you would see either the way outlined right here, or you would see delta S of the reaction, which is the same again as the system, is equal to the sum of the moles times the molar entropy of the products minus the sum of the moles times the molar entropy of the reactants. Okay, so a couple of things about this is that the equation that I've just written right here, oh gosh, I don't know if you can read that. Let's erase that. The equation right here, notice that in the equation is the standard, right? So it's telling you that these were formed at standard state, or this happened at standard state, which is not indicated in the problem, right? Also, I should outline that there is for delta S of the reaction, this is at standard state, and nowhere in the problem is it indicated that you are at standard state. So this is definitely not the equation that you use. I'm going to put a big red X through it. Do not use that equation. The other option is solving for delta S of the system is equal to Q rev over T. Now, another way that you would be able to determine that this is the equation that you're going to use is that the question says, or the problem states, that you want to calculate delta S of the system when this heat is removed reversibly. That little rev right here tells you the heat was removed reversibly, and it's always going to be at constant temperature. So you're going to be given one temperature. Okay, if it's not 298 K, if it's not 298 K, you cannot use the standard entropies in a chart. Those are going to be at 298 K. All right. So after that, after deciding what equation you're going to use, I'm going to plug in Q rev. So notice that the question says that 1108 joules is removed, or are removed, reversibly. So when it's removed, that means it lost heat, so that's where this negative comes into play. Divide it by 473 K, so 200 degrees Celsius plus 273 gives me 473 K. And so you should get an entropy of a negative 2.34 joules per Kelvin. Okay, moving on to problem number 2. Don't ask me about this weird red line. I don't know if you see that, but I see a weird red line running through this problem. Just ignore that. Number 2 says calculate delta S of the surroundings of 1 mole of ethanol vaporizing at 78.37 degrees Celsius given delta H of vaporization at standard state is 38.56 kilojoules per mole. The only equation that I outlined that has anything to do with the delta S of the surroundings is the equation outlined here. So this shouldn't be an issue in terms of determining which equation to use. So again, it has to be pertaining to the surroundings. delta S of the surroundings is equal to negative delta H of the system over temperature. So the tricky thing here then is not determining the equation, it's determining how to plug in delta S of the system when given delta H of vaporization. So how do those two have anything to do with each other? Well, it says that 1 mole of ethanol is vaporizing. So to give you an idea of what is happening, hopefully I can fit it in here. Let me put it down here. Ethanol, CH3, CH2OH. Liquid is in equilibrium or changing into the gaseous phase. So that is the reaction that's happening, and that corresponds with a delta H of vaporization of 38.56 kilojoules per mole. Since there is 1 mole of ethanol that is vaporizing, I can simply take my delta H of vaporization and multiply it by 1 mole. That gives me delta S of the system, which I can then plug in here into my equation. Okay, the only other piece that's missing is T. So I'm given that this is the boiling point of ethanol. The boiling point again is the point at which a liquid spontaneously vaporizes into the gas, and so I take my degrees Celsius, add 273 to get Kelvin, plug this temperature, again I didn't round until the end, so here I plug my temperature into the equation, and I get negative 110, indicating the decimal place to show that I have 3 sig figs right here, joules over Kelvin. Excellent. It should be a negative value. And this should make sense, because if something's being vaporized, that means heat is being put into the system. If heat is going into the system, then heat is leaving the surroundings. So if this is the surroundings and this is the system, Q is being transferred from the surroundings to the system. So essentially the system has a positive Q and the surroundings has a negative Q, which would make delta S of the surroundings negative. Your entropy of the surroundings would decrease. So you always want to make sure that conceptually it makes sense. All right, moving on to number 3. All right. Calculate delta G at standard state for the following reaction at 1000 degrees Celsius. A note I'd like to make here is standard state is at 298 unless otherwise stated. So this little degree sign right here means that everything in the reaction is either at 1 atm or 1 molar concentration. If it's a solid or a liquid, remember you plug in 1 into the Q or K expression anyway. All right, so there are 2 main, possibly 3, but really 2 main equations that you could have chosen to calculate for delta G naught. The other equation that you could have chosen from looking at the equation sheet is this one. Delta G naught, which you'll be familiar with as soon as I write it, is equal to the sum of the moles of delta G naught for the products minus the sum of the moles of delta G naught of the reactants. Okay, the reason why you cannot use this problem is because in that chart, the standard thermodynamic values, those are given at 298 K. This question asks you to solve for delta G at 1000 degrees C. So again, this is only at 298 K. All right, so in this case, I am not going to use this equation. The equation that I'm going to use is delta G of the system is equal to delta H of the system minus T delta S of the system. So in order to do that, And you have to plug in the temperature, which is already given, but I need to plug that in Kelvin. And I have to take or calculate delta H of the system and delta S of the surroundings. Sorry, delta S of the system. Okay, so I'm going to move this up just a little bit so you can see the standard thermodynamic data in this chart right here. So these values are given at 298 K, but I can correct for the temperature using the equation given. So to calculate delta H of the system, I'm going to take delta H of the products. So in this case, the products are magnesium 2+ and hydrogen. Here's hydrogen. Notice that for delta H it's 0 and magnesium is negative 467 kilojoules per mole. Again, notice the units. That's what I have plugged in here. And just to expedite this process, both magnesium solid and hydrogen ion are 0 delta G values. Delta H values that I've plugged in here. So that gives me a delta H of the system as negative 467. I'm going to do the same thing for delta S. So delta S of the products minus delta S of the reactants. So the only thing that you don't see here is any coefficients being multiplied by these values, because the only place that I have a non-1 coefficient is here with my H+ ion. And notice when I'm looking at H+ ion, both of these values are 0, so I don't need to multiply it by 2 here or here because it would still give me 0. So what I got for delta S of the system is negative 39.7 joules. Again, notice the units, joules per mole Kelvin. So I'm going to scroll up. I plugged in those values here. This is my delta H value, my delta S value that I've converted into kilojoules. When I insert the correct temperature in Kelvin, I get delta G of the reaction of a negative 4.16 times 10 to the second power kilojoules per mole, which means that at standard state at this temperature, the reaction is spontaneous because delta G is negative. All right, moving on to our last problem that has, I believe, 3 parts. This is the given equation. Nitrogen monoxide plus 1/2 oxygen gives nitrogen dioxide. And the K value, again, doesn't matter if it's Kp, Kc, whatever. In this case, it's going to be Kc. But the K value is 2 times 10 to the 6th. So the first question or the problem is to calculate delta G naught at 298 K. So one question that I didn't mention above, or one equation that I didn't mention above in question number 3 was the potential of using delta G naught equals negative RT ln K. So that is another delta G equation. The reason why you're not using that is because there's no value to plug in for K, so that's not going to be an option in question number 3. However, that is an option in problem number 4. So I have, in this case, 3 main options for delta G at 298 K. So because this is at 298 K, I could have either used, I could use any of these equations. Let me show you. So I could use delta G naught is equal to, and this again is of the reaction, the sum of the moles of delta G values for the products at standard state minus the sum of the moles of delta G naught of the reactants. You could use this equation. However, if the values for delta G are not given in a chart for nitrogen dioxide, oxygen, or nitrogen monoxide, it will not do you any good. Okay, so you're not going to be able to use this equation because you have no values for the products and reactants to plug in. However, if they are given, the delta G value that you would get here would be identical to the delta G that you would get here. So, in this case, it does not matter which one you use. However, I find that this equation, if K is given, is easier to use because there are fewer steps. Now, the other delta G equation that could be used is delta G naught I'm going to put of the reaction. And this is my ghost equation is equal to delta H naught minus T delta S naught. Now, you could also use this equation. Unfortunately, you have lots of options. Sometimes that makes things more difficult. But again, if delta S values and delta H values are not given in a thermodynamic data chart for this reaction that contains these compounds, then you're not able to solve for delta G of the reaction using this method. Again, the biggest indicator that this is the equation right here that you'd want to use is that K is given to you. If K is given, the easiest equation to use is the Great Link equation. So what I've done is I've plugged in my R constant in kilojoules times the temperature times the natural log of the K value given, and that gives me negative 3.6 times 10 to the first power kilojoules per mole. Great, so it's a simple step, although you have a couple of different options for equations. So let's look at part B. If the pressure of nitrogen dioxide is equal to 1 atmosphere, pressure of oxygen is equal to 0.5 atmosphere, and the pressure of nitrogen monoxide is equal to 0.25 atmosphere, will the reaction go right, left, or is it at equilibrium? Great. So because K is already given to me, really all I'm doing in this problem is comparing Q and K. So this is compare Q and K. This doesn't relate to any specific thermodynamic equation that was given in chapter 20. It's just comparing Q and K. So you would have to know how to set up the Q reaction quotient expression, which is always products. Right here, my product is nitrogen dioxide over reactants. So notice in the balanced equation, where we have it up here, that oxygen has 1/2 in front of it as a coefficient. There's a coefficient of 1 in front of nitrogen monoxide and 1 in front of nitrogen dioxide. So when I plug my values in, I'm going to have 0.5 atmosphere oxygen to the 1/2 power times 0.25 atmosphere for nitrogen monoxide. When I compute that, I get about 5.6. Again, this is unitless. Q and K values are unitless. So what does this mean? Although I didn't ask in part B for this much explanation, I did ask if the reaction will go right, left, or if it is at equilibrium. So because K equals 2.0 times 10 to the 6th, K is greater than Q. It's an ugly Q. Is greater than Q. So that means that the reaction is spontaneous to the right, or the reaction will go to the right to reach equilibrium. Okay, lastly, we're going to look at part C. What is delta G? Notice there is no delta G naught, so just delta G for the conditions given in B. Let me scroll this down just a bit so we still see what Q is. So for the potential equations is one is the equation given. You also could potentially use delta G equals delta H minus T delta S. Unfortunately, or fortunately in this case, delta H and delta S values are not given, so this is not an option. You could see this equation and you would ask yourself, do I have any values for delta H or delta S at the current conditions? You would not get these values from a chart, not from a thermodynamic table, because they are not at standard state. Okay, so this is not an option. Let's see, do you have another? These are your top 2 options for computing delta G. So that narrows it down to delta G equals delta G naught plus RT ln Q. All right, so in part A, you solved for delta G naught. Remember? I can scroll back down so you can see delta G naught for this equation is negative 3.6 times 10 to the first kilojoules per mole. And that again is at 1,000. No, it's not. It's at 298, sorry. 298 Kelvin. Perfect. Okay, so I'm going to scroll back up. All right, so what is delta G for the conditions given in B? I should have also indicated here that this is at 298 K. Okay, so that would need to be given to you. So I plug in delta G naught here, my R value in kilojoules per mole Kelvin here, 298 K here, and because it says the conditions given in B, my Q is going to be taken from what I solved for Q in part B, so that's what I have right here. And when I compute that, I get a delta G of negative 32 kilojoules per mole because, again, I'm not yet at equilibrium. I am continuing in that direction. That is it. If you have questions, email or text me. Good luck.